Today, more and more expressways are being built. These roads, which are really superhighways with all or almost all cross traffic eliminated, make possible the more rapid movement of a larger number of vehicles than conventional roadways. Although safety has been carefully engineered into these roads, heavy and high-speed traffic permits little margin for human error. All too many accidents are caused by drivers who are unfamiliar with the special skills and techniques necessary for safety on these superhighways. Use expressways only for traveling long distances. For short trips, use regular city streets. Make sure you have enough gasoline for your trip. Every year, over 1 million cars run out of gasoline on expressways. Also, check your tires. They should be in safe operating condition. A modern highway is a dangerous place for any type of breakdown. If you're not familiar with the location of entries and exits, check your map. Be careful not to mistake an exit for an entry. This can result in a head-on collision. In this film, we want to show you how to drive safely on heavily traveled expressways in or near cities. Getting on an expressway safely is the first problem you face. In some, the approaches and acceleration lanes are designed to permit vehicles entering to blend with through traffic without stopping. In others, you may be required to come to a full stop before entering the expressway. But regardless of the approach pattern, there are 3 safety precautions you should take. 1, realize that expressway traffic is moving much faster, sometimes twice as fast as traffic on a conventional street. 2, wait until a gap in traffic permits you to enter the expressway safely. 3, then accelerate rapidly and remain in the acceleration lane, matching your speed to that of other cars. Even where stop signs are omitted and acceleration lanes are provided, you should enter the expressway only when there is adequate clearance and you have adjusted your speed to that of oncoming traffic. Start your Drive-O Trainer cars and follow the actions of this driver. Did you remember to signal before you left the curb? He signals and moves into the left-hand lane in preparation for a left turn. He is going to turn left at the next intersection into a one-way street. He checks his mirror and signals again. Since he is turning into a one-way street, he enters the travel lane nearest the left curb. There's the entry ahead on the left. Signal and enter the on-ramp. Size up traffic situations on the expressway by glancing over your left shoulder. Adjust your speed accordingly to fit into a gap in traffic. Turn on left directional signal. Give left-hand signal. Glance over left shoulder. Slow down or speed up so that you can move into the extreme right-hand lane without conflicting with other traffic. Turn off your directional signal. Match your speed with that of other traffic. For safe driving on expressways, our driver observes the condition of traffic well ahead of him. This is often referred to as driving ahead of your car. Leave plenty of room between your car and the car ahead. Stopping distances are drastically lengthened with increased expressway speeds. Following the car ahead too closely causes most highway accidents. Seeing that car ahead slow down, our driver checks his mirror, signals, and brakes gently. Leave at least one car length between your car and the car ahead for every 10 miles an hour of your speed. Accidents at high speeds cause much more damage and personal injury than those at slower speeds. Now resume speed. The experienced driver who drives ahead of his car realizes how quickly at expressway speeds he can overtake slow-moving vehicles. Safe drivers pretend their cars are on tracks like a trolley and stay in their lane unless they are absolutely sure the way is clear for a safe lane change. Unable to pass because of overtaking vehicles, he signals and brakes, waiting until he can accelerate to the speed of the next lane. Unsafe lane changing is one of the leading causes of expressway accidents. He checks his mirror and glances over his shoulder. He signals, accelerates, and begins a slanting lane change. Whenever he passes on an expressway, the experienced driver stays alert for the potential danger of other vehicles, especially from the left. The expert driver not only drives ahead of his car, he checks his mirrors and glances to both sides from time to time so that he is constantly aware of the positions and actions of other vehicles. When the way is clear, he signals, looks over his right shoulder, and moves into the right-hand lane. Knowing how deceptive expressway speeds can be, he occasionally checks his speedometer to be sure he is neither speeding nor driving so slow that he is a hazard to following traffic. Now let's see how well you can drive on an expressway. This is the Hollywood Freeway. Defensive driving always pays off. Try to anticipate the actions of other drivers. When you see a driver caught behind a slow-moving vehicle like this, be prepared in case he changes lanes without warning. Check your mirror. Accelerator up. Now brake. If we hadn't been on the alert for danger ahead, there might have been an accident. It's important not to let your car wander out of its lane, especially on curves. Lack of skill or excessive speed usually causes this lack of control. Improper steering like this could have caused an accident if there had been another car in the left lane. The expert driver keeps his car centered in his own lane, except when he is deliberately changing lanes. One slow driver in a high-speed left-hand lane can force a number of other drivers into hazardous lane changing. Slower drivers should always keep to the right. Remember, an expressway is no place for a driver who does not or cannot keep pace with the flow of other traffic in any lane. In case of a breakdown or a flat tire, do not stop on the expressway. Pull well off the road to the nearest place of safety. It is better to ruin a tire than lose a life. When another car cuts in ahead of you and dangerously shortens your following distance, drop back to allow yourself adequate stopping room in case of emergency. The courteous driver does his best to help others at all times, especially on an expressway. Seeing that station wagon on the right, our driver signals a slowdown and drops back to allow the other car to enter the expressway. If we had been closer to the entry, we could have helped him best by accelerating somewhat to create a space behind us. Or had there been no traffic behind us and to our left, we might have been able to move into a left-hand lane before we reached the entry. Our driver knows he is getting close to his turnoff point. Because of heavy traffic to the right and behind him, he realizes that the safest way to change lanes is to accelerate into the space ahead of the cars on the right. He accelerates and gives right directional signal. He gives a hand signal, checks over his shoulder, and changes lanes. He turns off his directional signal. He matches the speed of other traffic. He signals and moves into the deceleration lane, maintaining his speed. He signals and slows down before entering that street. Our driver checks his speedometer occasionally because he knows that a driver who has become velocitized by expressway speeds has a tendency at first to exceed city speed limits. Park in the open space at the curb.
These 5 parts are steel. How would you join them? Specifications call for permanent joints and dimensional tolerances of plus or minus of 5,000. What about these cogs? How would you fasten them to the shaft if you had to do it quickly and maintain positive alignment? There are many ways to make joints such as these. The question is, which is the best way? A brief analysis of each joining problem will give you the answer, and the best solution frequently turns out to be the least expensive solution. First, ask yourself if an assembly would be taken apart at any time, or if it would be permanent. If it won't be permanent, some form of mechanical fastening, threading perhaps, is probably the best. Mechanical fastening may be the solution in cases where there will be need for permanency. But if the joint should be permanent, reliable, and inexpensive, one of the 4 permanent joining methods is indicated: adhesive bonding, soldering, brazing, or welding. Last, if the joint must be strong, such as holding the carbide tip on this punch, its strength approaching the strength of the base metal, only brazing or welding will do the job. Which is better? That depends. Here's an example. Some of the most complicated joining problems wind up here, in this very specialized job shop. Although cost is important in the jobs handled here, it is not always the prime consideration when clients ask for the complex technology available. Instead, clients want to be sure that each job is completed according to specification. So each job is handled separately, the best way possible, and often the only way possible. Like this one. 3 parts, 2 joints needed. Each joint must be permanent and strong. The size, configuration, and specifications have set the problem. Silver brazing is their solution. The assembly steps are planned, and a production run set up using a hydrogen atmosphere furnace. A high production volume can be achieved using this technique, and products meeting surgically clean specifications are the result. The brazing alloy penetration is complete, inside and out. Brazing is a flexible and versatile method of making a joint. It is unique, and it differs from soldering and welding in the temperatures at which it is done and the principles by which it operates. Soldering is done below 800 degrees Fahrenheit. It holds by adhesion, the gripping action of the molten solder in the surface irregularities of the base metals. Welding is a fusion process. Base metal and filler metal melted and fused together. Temperatures must be high enough to melt base metals and filler metal. In brazing, base metals are heated, and they in turn melt the filler metal. Brazing metal is drawn into and through the joint by capillary attraction, the same force that draws liquid into this sugar lump. Brazing is always done at temperatures below the melting point of the metals being joined. The strength of the brazed joint is derived from several factors, such as filler metal penetration of base metal capillaries and thickness of the brazing alloy layer. The strength of the base metals themselves, such as in this filter. Design of the structure adds strength, as in this gas meter housing, to ensure against gas leaks. And joint strength is derived from the degree to which base metals are wet by and alloyed with the filler metal. Brazing is frequently the optimum joining method for small and complex assemblies when joint strength is the major consideration, as in this aircraft hydraulic line, where joints are designed to provide maximum bonding surface for greatest strength. Or in this case, where an assembly station was set up for production runs. Preforms and special jigs speed assembly. After furnace brazing, each completed part must pass a 40 foot-pound torque test and hold up under 1,200 pounds air pressure per square inch for 2 minutes. The strength of a brazed joint is relative to many factors: size, configuration, design of joint, and strength of the metals being brazed. This brazing alloy, 50% silver, 15.5% copper, 16.5% zinc, and 18% cadmium, has a tensile strength of about 60,000 psi ordinarily. But it can produce a joint with more than double that strength. This rod is copper, and it's butt brazed. In tensile tests, the copper base metal fails. The brazed joint holds. Brazing does not affect the ductility of the base metals either. The joint is unaffected. With higher strength materials, such as steel, you can design joints for whatever strength you need, and brazing's capillarity will do the rest. Here are three common joints: butt, scarf, and overlap. For many jobs, the brazed butt joint will be strong enough. With the larger bonding surface of a scarf, brazing will give joint strength greater than the steel base metal. In a lap joint, too, strength is increased by enlarging the area of the joint. In many cases, the butt joint will be satisfactory, but where greater strength is needed, the lap or scarf joint is recommended. This principle can be put to good use in designing joints for specific strength purposes. These basic principles apply in joining any metals by brazing, even dissimilar metals. And this means you can use the materials best suited for their function in any particular assembly. In this gas bobbin, for example, stainless steel of two types, ambrac and copper, are joined in a single operation. Brazing is flexible and versatile enough to solve many special joining problems, as you've seen. But what about brazing as a mass production technique? In case after case where high production rates and low unit costs are the prime considerations, brazing has been the answer. In this example, steel soldering gun tips are brazed to copper terminals at a 4,000 per day rate. Fan assemblies are brazed here, one every 6 seconds. In this case, air valves are assembled at a rate of 12 per minute by brazing. In another plant, 650 appliance fittings are automatically brazed each hour. And here, car heaters are manufactured for one of the big three in the automotive industry. Unit costs are measured in mils, and production techniques are planned for highest efficiency. This is an automatic station designed by the plant methods engineer to braze two tubes to a header. Two probes penetrate the piece, and a predetermined length of alloy is automatically fed into position. Heat and capillary attraction do the rest. At this station, one man can turn out 200 units per hour. No setup time is required. Every 18 seconds, the automatic brazing rig joins two tubes to a header in one step. At another station where a more complex unit is brazed, preformed and prefluxed rings help speed production. Gas-air heat is being used, and capillarity again does the work. Tubes and headers are brazed together to provide a strong joint at the critical point. Where joint strength is less critical, as in joining end pieces to the core section, soft soldering is used. In tooling up for production runs, you can take advantage of brazing's tremendous versatility. And the range of alloy forms, shapes, and compositions is almost limitless. Only two basic requirements need to be satisfied in making a braze. The filler metal must be compatible with the base metals and melt at lower temperatures. For example, these are 5 of the many precious metal brazing alloys, each different in its melting characteristics. Sluggish alloys work best where fit-ups are variable, free-flowing where parts are close-fitting. At this plant, both types are used in the furnace brazing, which is their specialty. Before setting up a production run, tests are made to determine optimum balance between heating temperature and time, as well as behavior of brazing alloy. Each joining problem is analyzed in advance to find the fastest and cheapest way to braze. With a variety of furnaces available, odd sizes and shapes can be handled with ease. Since in brazing, heat is applied to the base metal, not the filler, a number of heating methods can be used. Existing facilities can often be adapted without difficulty. Induction heating on single or multiple element units is frequently the most efficient technique. Salt bath or molten metal heating work well, as do gas, air, and torch methods. In fact, practically any method will work, and you can use whichever is best for your situation. Now, what about this job? Close tolerances must be maintained. Joints must be permanent and strong. Brazing is the best solution. First, careful positioning. Then preforms are set in place, and it is brazed in one step. The completed part is clean and strong, and tolerances have been maintained. It will perform as specified. And in this more common case, what's the quickest and most efficient method to align the cogs on the shaft? You could set the cog in a jig, drill it, thread it, insert a set screw, and tighten, or braze it. Which way is easier and more positive? Any joining problem, even the most common, deserves a little analysis. Whatever the answer, if it's right, you'll find that you get a bonus for your effort, lower costs. If your analysis shows that brazing is a strong possibility in your production, and you would like to investigate it further, we at Handy & Harmon are able to help with suggestions regarding design, production, metallurgical considerations, and heating techniques. After all, we are the leading manufacturer of brazing alloys and fluxes. A question of feasibility? Call us, and one of our field engineers will stop in to talk with you. Or send us parts, and we'll see what we can do. Perhaps recommend a design change to break a unit into more easily made components. These parts can be brazed in one step. When you braze, there is no loss of strength, conductivity, ductility, or whatever operational properties you require. Certainly, we'll test braze it, analyze results, and be of whatever help we can. These are some of the services we provide to help you take advantage of brazing. Manufacturers in many fields, producing a wide variety of products, with every joining problem imaginable, have found brazing the best solution. It provides strong, permanent joints, leak tightness, ductility, good conductivity, corrosion resistance, and low per-unit costs. Will brazing help you solve your problem? Why not get in touch with us, and we'll examine it with you.